All right, so as shown here, I work at Twitter. I work on infrastructure stuff, and I'm pretty excited about like MapReduce systems and big data analytics systems. The last talk, really awesome. Like we're trying to use things like the Countman sketch in our jobs. That's kind of what I'm going to talk about today. So as a bit of background, I've worked on and written a bunch of open source around MapReduce systems for a couple of years now. I maintained Cascalog for a while, which is kind of a closure layer over top of Hadoop. I've worked on scalding, on various ways of processing these big data systems and running MapReduce jobs, and also different like storage layers for how do you store this stuff, how do you build clients, how do you serve this data out. All of these problems are, I think, related, and we're going to talk about those today. So this is less of an algorithmic talk. I don't really have any proofs in here. This is more about good engineering practices at scale and some of the things we've done that make it easy to use things like the Countman sketch in distributed systems and not have to deal with all the pains that you might be worried about when you go to more complicated things like this. So specifically, I want to talk about this library called Summingbird that we've been working on at Twitter. What Summingbird is a little library that lets you write a MapReduce computation in what looks like kind of Java or Scala manipulations of collections. You've got your map, your filter, your flat map, all these things in familiar code. Then Summingbird will take that job and run it on a MapReduce platform like Hadoop. So there are a lot of libraries that do this. Scalding does this, Scooby, Cascading was designed for this. Many libraries are aimed at making Hadoop jobs easier to write. What Summingbird adds to this space is the ability to take the same job that ran on the Hadoop cluster, also run it in some sort of real-time MapReduce platform like Storm or Akka or a message passing system or things like that. We wanted to kind of capture the idea of a streaming aggregation and separate that out from all the systems issues that are associated with that thing. Specifically, we want to enable more complicated aggregations than we've been seeing in a lot of the open source examples that are out there for Hadoop. But so I'm going to go through, as a structure of this talk, I'm going to go through a little bit about MapReduce and then some of the libraries we developed that make it easy to use things like Countman sketch and some of these data structures in your systems. So who's used Hadoop before? Who here, like I saw a Hadoop cluster open in the back, so you guys are pretty familiar. I'm going to give a quick overview of MapReduce and why kind of we chose this model to implement Summingbird in. This is word count written in Summingbird. Everybody who talks about Hadoop has to do a word count tutorial. It's like the simplest aggregation possible. They're all over the place. So this is my contribution to the word count space. So this is Summingbird. We can go ahead and show word count in. This is what it looks like in Hadoop, and I've highlighted here the job logic, kind of the non-systems pieces of the code. It's kind of like a cheap shot because of what, but I have to take it. That's the taking words, like taking a string, parsing it out into words, and writing it. This is the actual reduce function that we'll talk about. This is Storm, which is a similar kind of MapReduce platform that runs in real time on streams of data. So it gets sort of one piece of data at a time, whereas Hadoop processes big batches of data. This is the same logic that we've looked at. We've got some mapping, some reducing going on. And, this is Summingbird. Again, there's a little bit of code required to run the job in a Hadoop world versus running it in Storm, but the job logic is the same in both of these cases. And what we're going to talk about today is kind of how this ability to share code and share ideas makes it easy to not just sort of split computations between the batch and the real-time world, but really do really complicated stuff with the data structures we are interested in for streaming algorithms. Okay, so quick overview, I'll speed through this. You guys seem pretty familiar. Map and reduce are what's MapReduce? It's the map and the reduce. So the map stage is really about taking your data, your tweets, your ad impressions, your whatever, and getting them into some sort of key value form in which an aggregation can occur. So Hadoop's really good at, if you give it keys and values, taking your data, grouping by the key, and smashing all the values down together with some sort of associative operation. So word count, our values are counts, and our keys are going to be the word that you're counting. So I don't know if you guys are the map kind of came from the functional programming world. So these are the three operations pretty much that Summingbird supports, and Summingbird can work with any MapReduce platform that can kind of talk about these operations. So flat map is really this idea of like quickly to go over these. If you have your stream of data, you all know about map, like each item in the stream kind of gets mapped to like some other item. Filter drops things out of the stream. Flat map is kind of the more general version of both of those, where each item gets mapped to like a number of items, and then those all get sewed together by the system. So this is how you like expand your space. So that's the map of MapReduce. Word count, we'll skim this. Start with tweets. The flat map generates these lists of word to count, and then what a MapReduce system does is groups together all the values for each key into a little list, and then sums it down with some reduce operation. So these are the kinds of things we want to support. Specifically, we want to support like much more complicated things than this. We want those ones to be like countman sketch instances, hyperlog logs. If you can talk in this model about more complicated aggregations and have it make sense in a real time in a batch world, like you're good to go. You can do some really powerful stuff. So this is like my little MapReduce drawing I made. Again, the flat map is about getting the keys and values that we want to aggregate. And Summingbird specifically allows you to write sort of multiple MapReduce topologies and then have a client, like based on different systems properties, either go to Hadoop for sort of more reliable data or Storm for real-time data. So we're going to motivate these more complicated aggregations by sort of showing like a pretty easy one. So this is like a product built on word count. It's Google's Ngram viewer. It's, like you can see it goes back to 1800, but like we could imagine this as a real-time system. Like you really need to know like all the words in every tweet. It's got to be reliable. It's got to be up to the minute. This is like the kind of trivial application that will motivate the non-trivial ones. So here's our word count job again. A typical, let me tell you guys like how a Hadoop system's designed typically. Like data comes in, Hadoop processes these big batches of data. So your system buffers up data in logs or something and kind of waits till enough like tweets are around or whatever. And then Hadoop will sort of fire up on a clock, go take all this data out, run your flat map function on it, and then do the reductions and like sync the new counts into some database. So what we're seeing here is like by hour counts of the word ape. So every time your Hadoop job runs, you get kind of a new batch of data jumping forward, and whatever dashboard you're powering like jumps forward a little bit. So that's good, but we're missing this sort of real-time component that we want. We want to power dashboards, analytics dashboards that have specifically the real-time side. So skimming this stuff, like Storm gives you that ability to, up to the second, like process all the data that comes in. The problem with a world like that is the databases you typically have to use with Storm, like Memcache, Redis, these things are much less resistant to faults than a serving architecture for a Hadoop job. So you can lose data, it's harder to work in a real-time only world. So ideally what you want is a system that can talk about both at the same time, and a smart client that can switch between data calculated by Storm, as we see in the red, and data calculated by a system like Hadoop, and really provide kind of a seamless view over top of these things. So you want to move this sort of, allow this client to pull most of its data from the top of the picture, a little bit of data from the bottom of the picture. So like, what's hard about that? Specifically, if we want to move beyond the trivial example of counts, like what kinds of things can we aggregate here? Summingbird gives us the tools to take our MapReduce job and run it in real time in batch. That necessarily comes with a number of constraints. So the question is like, what is the constraint on the types of values you can work with in the system? And I think that this is the key for like really merging with academia. And like when we mine these concepts, this is the question we have to ask, like which concepts can we actually pull out? So it turns out that this little interface called the monoid is like the key to streaming MapReduce aggregations. We thought a lot about like the simplest possible idea that you could really plug in like all over these Hadoop jobs. It turned out the monoid was the one. Monoid, super simple interface, as you can see. You define a plus, which is an associative operation, basically like tell me how to combine two of your things. For numbers, that would be like plus, right? For sets, it would be union. For hyperlog, you can imagine taking the byte arrays that back two hyperlog instances, and for each index, just summing the counts there. So you end up with sort of two smaller hyperlog. You can merge these things together, and it makes just as much sense. We also need a 0, which when merged into the bigger data structure, it doesn't affect it at all. So this sort of identity operation. We need to be associative. And to answer the question of what types of values you can use in this thing, we implemented a bunch of values that kind of have monoids on them, and we open sourced them in this library called Algebird. So this was like such a useful concept that it turned out at Twitter we could enable like dozens of different applications by writing monoids and writing data structures that we could combine. So this is Algebird. This is open source now. A ton of people are using it. Some of the data structures we have here that you can run and you can like use in MapReduce jobs are like average values. We've got Bloom filters. We've got a hyperlog. We've got a countman sketch. You know, all sorts of things. So when our engineers go and they want to write streaming MapReduce algorithms and build these dashboards, this is kind of like how they start thinking about the problems they want to work on. And the ability to just take one of these things, like a countman sketch, and not think about the systems issues that go into using this is very, very powerful. So the monoid. Go through a couple. As I said, this is the, you know, straight up like addition monoid. This is how you add numbers, just with plus. We've kind of broken it out of the actual like int implementation or number implementation into this interface that we can go pass around and reuse in Hadoop. This is the monoid on sets. Set monoid is like set concatenation. And you know, there's the example at the top. The empty set is kind of the identity in that. Map monoid is a more interesting one. So like, say you want to use a map, whether it be an approximate map or a hash map. The way you would merge one of those is if there's ever a clash between the keys, you take recursively the monoid on the sub-value and use that to combine the two. So these monoids compose really nicely. You can imagine, as we'll talk about, like a map of some sort of key to a value, which is a countman sketch, which itself is used. And so you can really build, like with these primitives, like pretty intense systems. This is one that people love around the office. The multiplication, actually a monoid as well. Like multiplication is an associative operation. The 0 is 1, kind of confusing, but like totally valid within this framework. You know, it's a constraint, but it allows a lot of different ways of computing. Yeah, so I want to show kind of where this is used in the system. The idea of the monoid like enables the reduces in Storm and in Hadoop. So the reduce that we talked about in MapReduce, you can also plug it in to the flat maps to get these nice like map side aggregations. A lot of the systems issues behind like scaling this stuff turn out to be very related to this monoid problem. So you can use the monoid to get not only systems that are correct across this sort of batch real-time boundary, but are very, very fast. And like the other place that the monoid is used is the client, when it has to go fetch from these Hadoop and Storm stores, now has a way to kind of reconcile the data between the two. So what can you build with this stuff? Quick story about, you know, we spent a lot of time like implementing these monoids, building out this library, and it was a little abstract, and you know, people were confused, I guess, at first about this idea that you could just take one of these data structures and just plug it in. So we had an intern come to us and ask about, he wanted to build an application that was, you know, tweets get embedded all around the web. So you can take a tweet, stick it on a website, and then people will come and look at those tweets and give them impressions. So the product he wanted to build was, when a user comes and looks at a tweet, for each tweet we want to maintain a hash map of URL to the impression count for like how many people at that URL saw the thing. So for most tweets that get embedded, you can just use a hash map, totally fine. Your counts are going to be small, not that many people embed the average tweet. Some tweets get embedded everywhere. A lot of the Boston bombing tweets were embedded, you know, all over the world on many, many sites. And this hash map gets enormous. So he wanted a data structure which would give him, you know, look like a hash map, give him approximate counts, and also, you know, if maybe we could like accommodate it, he'd like to be able to look up like the top K sites that had embedded something. So it was one of these like, you know, countman sketch, no problem, plug it in, this implementation we had kind of at the ready by recognizing this monoid idea and implementing a bunch of data structures, let him do this crazy thing. So it became kind of a joke around the office, just like monoids for everything. Monoids were became like a drinking game, like monoids, and it let us do all sorts of crazy stuff that really freed us of the systems issues in a really important way. So that's open source. That's in a library called Algebird. You guys should go look at it. You should use these. Really, really cool. You can plug these in now to your Hadoop jobs, your Storm jobs. You don't need to use them in Summingbird, but they're very powerful for MapReduce. So we've got the system now where we've got a lot of implementations of these things. What if you have some data store that requires JSON, or the serialization is a little weird? How do you actually use these monoids and these Countman sketch implementations in your job? This was kind of the next problem we needed to solve. The systems issue of all these lines, serializations occurring. When you're doing these merges and everything, you're actually, you need to store this stuff in a database in a way that makes sense for later. So we tackled that with another idea from functional programming, turned out to be very, very fruitful, called the injection. So injection here is kind of like a function, except it can sometimes go backwards. So you can think of serialization like this. You take your number, your Countman sketch, or whatever, you go to bytes, and then maybe you can come back. Not all byte arrays can deserialize to what you want. The reason we put this in its own trait, the reason we have this interface that is not just the function, is that one, people were doing this all over the place. This is a really basic one. This is turning a long into a byte array strings. When it's easy, you recreate all this code and you end up making errors, and it's a problem. The other thing that this enabled was these injections turn out to be composable, right? So you can take two of these things, A to B and B to C, and you can make a new injection which gets you all the way through and then maybe all the way back. So if you're using a Countman sketch object, you don't want to Java serialize it or something, and you've got a thrift representation of this thing, you can go ahead and serialize your Countman sketch through this thrift object into byte arrays. Your code can kind of keep talking about Countman sketch, keep talking about all these things, but under the hood, the bytes are sort of in a form that makes sense for long term, maybe stored as JSON, maybe able to be interpreted by a Ruby app that can read out a Countman sketch and do its own algorithms on it. So the monoids allow you to do these more complex aggregations. In theory, they let you combine these things, and this injection idea lets you actually use this stuff in real systems. An interesting thing that comes out of this, another property I want to talk about, this is crazy Scala code. We're not going to get into it. The idea here is that if I have a bijection, a way of switching between two types, and I have one type is more complicated, one type is less complicated, I can actually take my monoid on the trivial type, like a number, and create a new monoid on the non-trivial type. So this really opens the space of aggregations you can do. One bijection that one of our guys wrote was numbers, integers to English language integers, right? So say you want to build a dashboard which doesn't show you numbers, it shows you English language representation of counts. So 1 to 10 can actually print out as the strings 1 to 10, and we can go ahead and convert our integer monoid to an English language monoid. So the English language stuff, it's kind of hard to figure out what a monoid is on that. Super easy to figure out the integers. So this monoid now allows us to take these English integers and add them together. In kind of crazy ways. I don't know of any dashboards that are using this stuff now, but this is kind of, the example you can extrapolate is taking some simple thing from which you can derive a Countman sketch object. So we released this as an open source library as well. It's called bijection. It's got a lot of the standard stuff you use, if you want to serialize JSON, if you want to serialize protobufs, thrifts, all these things. This plus the monoids is kind of all you need to really start using a lot of these functional programming ideas and in your MapReduce pipelines and in your streaming analysis. So that's out in the open source world. And the final thing, the final piece of the picture that a system like Summingbird leaves to the user, which is like kind of a problem, is the client here is now responsible for like delegating out to each of these underlying stores, right? So like if I'm the client, I'm building my dashboard, I want to go ahead and fetch like some data from Hadoop, some data from Storm. Which data do I get from where? How do I like do this? You want to be able to hide that from the user. If you're going to ask the user and like give this nice property of like being able to run your job on different systems and in different execution platforms, you need to kind of marshal everything together at the end. It's important to do that. What we want is we want a store basically that can pull data from each of those under the hood and make that decision sort of a systems issue and not have the client be concerned with it at all. So the final this was the final abstraction, I'd say, that was required to build a system like Summingbird that could run in Storm and Hadoop and have the results kind of make sense. So we did it. We implemented super simple key value store. Basically has a get and a multi-get, and you can go ahead and implement this interface for like most of the key value stores you know. This one's interesting because you can define a monoid on this thing. So I can add two of my key value stores together, one of which talks to Storm, one of which talks to Hadoop, and you get at the end of the day kind of this like combined store, which is the same type as your original stores. So the idea of store combinators was interesting. This is how you sort of merge data between these two like online and offline systems. It turned out that this idea was also useful in caching over different stores. So say you want to take a store and like add a cache to it. That's a really nice store combinator. You also sort of have a store at the end of that. Logging became really important too. So we, took this idea of this merge that we needed to do and flesh this out with a bunch of other kind of tools you can use to build clients with these systems. Logging being like a big one. You can have stores that sort of kick out to visualization graphs, monitoring stores, all these things, and we released a library for that too. So this is Storehouse. This is out in the open source world. This works very, very well. I would say this is a key value store which is kind of designed with aggregations in mind. The idea is that if you use this store with these kind of other tools, these stores know how to deserialize your count min sketch and your more interesting objects you've aggregated and merge together across multiple platforms, and really sort of enables you to not just run pipelines on this stuff, but build applications on top of this stuff. So that's our key value store. And so what's left? Summingbird is kind of just the glue layer that like pulls all this stuff together. And we're going to open source that at the end of July. So there's not really much you need to build beyond these systems to like create the actual graph that compiles down to Storm and Hadoop. But we're planning on getting that out in the world, and we want you all to use it and try it out. So what's next? We're going to open source this thing. We're going to get it out there. We're going to have a lot of sort of demos of how to use this stuff, how to use these more complicated aggregations. We want to add like new execution platforms. Like there's no reason that this system shouldn't be able to run on like Akka or Spark, some of the stuff the Berkeley guys have been working on. And finally, now that this kind of abstracts the systems issues, one world that's opened up to us is this world of, we can really sort of take a system like Storm that runs real-time computations and teach it to kind of auto-scale and, filter data for us and do all sorts of interesting things. So, so what's next is really just getting this thing out there and, giving the world a system that can allow you guys to go ahead and take all the stuff we talk about today, these new interesting aggregation techniques, and like use them in the real world and build stuff at any scale on them. So it's pretty quick. I think I covered a lot of these different elements of the system. I guess what questions you guys have on kind of the motivation for this and what's going on? Yeah. Yeah, this is a good question. This is kind of the motivation for all of this was, as you said, to make it like really, really easy to write a job that looked like kind of an algorithm you'd describe. Like take this data, parse it out into like this key and this countman sketch value, and then like run the data. So yeah, it has made it easier. This intern I was talking about who came to us with the countman sketch problem, we sat down like that afternoon, and this was early in Summingbird, so not everything was ironed out, but we were able to kind of write the job he wanted, get it running on the Hadoop cluster immediately, and have him serving data out to kind of a local test cluster right away. The blocker to that project became like finding him a couple of Memcache machines to store his data in because he was ready so fast. Yeah, so it's really made it like almost trivial to go ahead and write these things, and you find that like people around our group now are reaching for these things very, very easily because the issues that always stop people were how do you make these things go fast? How do you scale a system that's backed by something like a countman sketch? And how do you build like clients on top of these things that can just rely on their properties and know that these things are going to be available and around for long term? Yeah.
Sorry, I guess like the follow up is like with that case you mentioned, the intern project, like kind of got into before it was really easy to not do that with countman sketch. Actually have all those tools and throw away the ones you don't care about. Like did you reach for this because you guys were like, hey, this is there, or you saw it?
Well, he reached for that one because particularly like at Twitter, we have just these huge skews of data. And so like conceptually, he wanted to reach for a map, right? He wanted to just go ahead and like build up these URL count pairs. But the systems issue that, this is sort of a mid-level thing. And like the systems issue that he ran into was that the clusters we were dealing with, like the values of these actual hash maps to store all these counts was just getting enormous. Like on some cases, we're talking like 2, 3, 4, 5 megs for the values. So, he was still kind of exposed to the systems issue at the level of Summingbird, but he came to us saying like, how can I deal with this data skew? And the answer was, you can take this data structure which can switch over to a countman sketch sort of when the data gets too big. But the talk was at that level rather than, we need to go ahead and like build a whole totally custom solution because we only know how to count numbers. And like, you're on your own on a storm topology. Good luck. But yeah. Mm-hmm. Yeah. Yeah, so the two things we needed to share between Storm and like a Storm job and a Hadoop job really were like the flat map function and then the monoid to do the reduce. So, we were working in Scala, but in Java, you can pretty much describe like the function is kind of a good enough abstraction to talk about the actual mapping. And each of these systems that we compile down to like kind of have their own custom versions of functions. Like Storm has bolts, Hadoop has its like map, but you can go ahead and build out like a single Storm topology that just has these little plugs for like stick the monoid here, stick the function here, go ahead and like have a hook for the config, and then you're done. So basically what we did for that is we wrote one Storm topology and one Hadoop job that knew about functions and monoids, and then that was it. And that's all you would have to do to run this thing on like a different execution platform. Does that answer the question?
So I think that the follow-up that is kind of wide out from last member, like for example, you still need to write a Scala code that better tell line the underline, right?
Yeah.
So it's a wide out of one separate function like SQL. So anything that is one line.
If you just wrote like a SQL query?
Right. Well, I can see that and you come back the SQL semantic
I guess my thought on that is like the problem we were solving was how to kind of reconcile these two different like Storm and Hadoop, these execution platforms, in a way where you still had kind of rich control over what you were doing. Because once you get up to a level where you're just doing like one-line queries, things get when you have systems like this that want to keep counts but maybe need to switch between a countman sketch and a map, like it's hard to describe those optimizations. So the goal was kind of to put like an abstraction layer over which you could build things like that. And in fact, we have a group at Twitter building a system on top of Summingbird, which allows you to say, I want this data stream, and I want point to some fields in a thrift object and say I want unique counts of this, I want exact counts of this, and I want like the skew of this value. And then we can go figure out like all of the monoids necessary and kind of do all the pick and choose. Yeah.
What are because you're talking to a lot of systems, like what are the actual performance characteristics that of your systems? Like I saw you have MySQL there, like you have say merge data, do MySQL just the one like whatever how.
Yeah, sure. So the motivation for like why would you do this, right? You have like this batch and this real-time system. Why would you not just work straight in Hadoop or in Storm or in one system? And what sort of issues come into play when you like merge these two, sort of merge across data stores? And the answer to that is that each application kind of has different requirements for this stuff. For example, like in local testing, you might want to run Summingbird just totally in memory. MySQL, as you said, is like not good for big applications. For smaller applications, it's really nice, and it's just easier sometimes to run these things. So by, I guess, like abstracting over these issues, the performance characteristics are sort of like a function of the backing stores that you choose, and they do become kind of a systems issue rather than the actual application code. So like realistically, the performance that we're seeing is pretty good. The data stores that serve data from Hadoop are read-only, so they're all kind of hovering in memory and have very, very low latency. And then we're able to put all of the real-time data we serve for these dashboards in something like Memcache. So the latencies we get are like really, really low. And for most data, you can read directly out of only one store. You don't have to do any merge at all. So like at the end of the day, these things are really, really fast, and they kind of can compensate for one another. If your Hadoop job breaks, you read more data out of online. Yeah.
I was just wondering Hadoop job breaks kind of motivates this. Since you have all this sort of algebraic structure of sort of there in common, is there any sort of clever solutions for data redundancy and failure recovery? Like kind of think using monoids, XORs of monoids. It feels like there's something there.
It does feel. I know it does feel like there's something there. The big win as far as data, like we definitely haven't gone down to the level with this project of these like deep systems things of like how could you use this algebraic structure like of the bytes within this particular data store. We do find that like for data recovery issues, like sometimes you realize that like all of the data you've calculated is wrong. For example, like an analytics dashboard where you're counting like clicks, you realize half of these clicks are from bots, things like that. You can go ahead over your like entire backing store and sort of reuse these algebraic structures, and basically like as you're doing a recompute, merge in sort of good data, bad data, all these things. So it stretches kind of beyond this like these two links. Really what we've designed here, like the goal was to design a system that could ideally on like a key by key basis go to whichever data store had kind of the best promise for like latency or data correctness or what have you.
So you mentioned the example of the case with the URL counts that explode out from normal map to maybe a CM sketch.
Yeah.
To what extent are you guys kind of leaning into that safety clause given the DAS issues at Twitter? Is that the default option is to use kind of things that have high precision for low cardinality and then explode out with something that's much safer but will give you an accurate sketch? Or is the default kind of just the normal bad types that you run into and then every once in a while something blows up in production?
So up to like last year, I would say the default was just straight up exact counts for everything. And, even like the features that were going into our models and things like this were like very exact, and we used Hadoop for all these things. And as a result, like a lot of systems were really, really stressed because it's hard to keep exact counts for everything. You have to keep a lot of data around. So it used to be that the default was exact stuff. And I would say that with this project and with kind of the thinking that we've been doing lately, we're starting to default more to actually using a lot of the approximate algorithms. Like if you look at how data flows through Twitter, like 5% of data or like some percentage of data is going to get dropped coming in from the client anyways. So like the meaning of like an exact count on an analytics dashboard or like impression counts, it's actually pretty ill-founded. So anything that touches like advertisers or billing or things like this, we play it safe, we keep the exact counts. But for a lot more of these like trend detection and machine learning algorithms, the Countman sketch and the approximate data structures have been like hugely helpful. Uh-huh. Yeah, it's called the eventually monoid, and so you wrap this thing, you like have an eventually monoid that is like a map, eventually a Countman sketch, and you create like an instance of that, right? And so the monoid on eventually is you have this function which determines like when you make the switch, so it might be some size of like a set. So, sets are getting aggregated, like things are good, but if one of them comes in and tips the balance, then from then on, anything you merge into that thing will be the approximate data structure. So that's the kind of thing that you can like totally abstract over. You could say that like, aside from the slight overhead of wrapping this thing, like you could treat everything as an eventually data structure, and then you'd be like good to go, and you'd essentially cap yourself for these size issues.
So these approximate data structures carry around and combine with one another information about certainty, like the calibration of how approximate they are.
Yeah, they do. A lot of times, like, the Countman sketch uncertainty is a function of like the size of the Countman sketch you allocate. And so the monoid is sort of calibrated to combine Countman sketches of a certain size, things like this. So a lot of the data structures we see here, like the average value or things like this, like carry around kind of more metadata than you'd actually use in a client. So the average value keeps like a count, and then the average up to that point. So when you combine these things, you end up doing a weighted average. So like you get these more rich data structures in your values, and what the client can do then is query that thing and kind of do the final operation to pull that information out. In your example, you might go ahead and like query some sort of data structure and then either present the error bounds or like return nothing if the error is above a certain rate. Yeah. Yeah, that's not something that like this existing paradigm bakes in anywhere. The question is, can you take the errors that are like that Storm introduces just as a function of like the Storm cluster went down or your queue broke or something like that, and actually like store that along with your values. I think that is related to this question of can a value carry along like information about the error. I mean, we don't have it now, but like you could imagine like a Storm mode of execution where if the data flow got like too much for Storm, it started dropping events and then logging this sort of what happened along with the values it was kicking out. So we don't have that now, but like that's a really interesting question, and it's something we have to deal with where like we know that this data is bad, but like how bad is it? And do we have to go to this other Storm cluster or things like that? So yeah, good question. Yeah, so that's something I kind of covered over here. I'll answer that briefly. Like for time series data, it's pretty easy because fundamentally your time series works like your graph is going to work in these steps of like every key is segmented by hour or something like this. So when your Hadoop job runs, basically the Summingbird Hadoop job is very careful to only consume data that filter all data that like only go up to a certain batch, we call it. So I'm only going to process hours like 5 through 8. And anything that occurs after that hour gets filtered out. And so the data we store in sort of Hadoop serving layer is not actually just a key value pair. It's a key to a pair of value and like the batch up to which we've processed. So on a key by key basis, the way that the stores are actually merged is look up the key, get back the value, and also some metadata about where to start querying like memcache from. And it turns out you can do this for non-time series data that sort of has all time counts. You can just artificially sort of segment your data in the online, in like a memcache store, and then the client, these smart clients that merge, can go ahead and like do the logic and present you with your key value. Does that make sense? And that's part of kind of the last thing that's baked into Summingbird is the particular implementations of the Storm job and the Hadoop job that we run are both aware of this fact and store enough metadata that you can really like merge these things. And if certain systems start to fall behind or become more faulty, the client, knows how to go fix those issues. Yeah.
Slightly different topic. What have you not been able to do on this? What's the last thing you got asked to do?
That we can't do on this? Specifically, yeah. So, I mean, like, this question is, we started this project kind of like gleefully accepting constraints to the problem. One thing that we were asked to do recently that is kind of hard to imagine is like this idea of like an inner join across different streams. So we talked here about MapReduce. Like some operations are kind of hard. It's kind of hard to like imagine what they mean in a real-time context. Like when you talk about doing a join in Hadoop, you go ahead and you can like, or in like a SQL table or some sort of database, you can go look at the two tables, perform the join. The data is like there or not. In the streaming world, it's not really like clear what that means. And so some of these things, like once you run into multi-stage MapReduce jobs where you aggregate some key value pair and then you want to like flip the key and the value and then aggregate again on something else, like those questions are kind of ill-founded. So people like that's kind of like the hole in this problem. People come to us and say, can you do this multi-stage thing? Can you do that? And the answer is no, and that's fine because by limiting the problem and requiring sort of, for now, one MapReduce pass, a limited number of operations, and like you have to give us a monoid, we enable like probably like 80-90% of the things people want to do. I haven't looked at it yet, but I know Spark pretty well. And yeah, they're definitely coming out with a lot of stuff around this. I may be wrong. I probably shouldn't even be saying this. I think that a lot of the other takes I've seen on this problem involve taking a system like Spark and kind of modifying it to handle both of these cases. And that's cool. It's really exciting to see kind of new systems that tackle both of these problems. The goal of this library was more to accommodate the existing systems that you guys have. So take a particular job written in a certain way and like run it on your cluster, run it on your akka cluster, not sort of require a full ingestion of like the philosophy of, all you need to accept is kind of MapReduce and then that's it. Cool. Yeah, thanks guys.